In this second lesson on thermometry, we're going to look at the use of some temperature measuring devices, but first let's briefly discuss the challenges in measuring a temperature accurately. So consider the example shown. We have a beaker of ice water and we have a thermometer immersed in it, and we're trying to measure the temperature of the ice water accurately. Now, if the thermometer is located in the center of the beaker at the surface of the ice, then there's a pretty good chance that we'll be measuring a temperature very close to 0 degrees C. But you can probably appreciate that if we had a thermometer that was situated against the side of the beaker, like so, and consider that perhaps the temperature outside the beaker was, say, room temperature, let's say it's 20 degrees Celsius. You can appreciate that the outside temperature at the surface of the glass is 20. It'll gradually decrease across the thickness of the glass and be 0 somewhere on the inside. But if the thermometer is touching the side of the wall, well, that temperature may be slightly higher than 0 degrees C. And so the point is simply that the location of a temperature sensor is very important. Let's consider the steady state of the sensor. The steady state of the thermometer bulb would be constant when the rate of heat conduction away from the sensor is equal to the rate of heat conduction to the sensor. Now, glass is a poor conductor, so it would conduct heat very slowly to or from the sample, whereas temperature sensors made of metal would equilibrate rapidly because they're rapid thermal conductors. So there's a time factor there. Lag, if the temperature of the sample changes, then the temperature of the sensor will not change instantly. Again, glass equilibrates slowly, whereas metals equilibrate quickly. It's possible to disturb the temperature of the sample with the sensor. Now, let me give you some exaggerated example. If I wanted to measure the temperature of a snowflake, I went outside with a glass thermometer, and by some feat of dexterity, I was actually able to get a snowflake to land on the sensor of a thermometer bulb. I might find that, in fact, the snowflake melts. And so actually I've disturbed the temperature of the sample by the mass of the sensor. So it's a consideration when you're trying to measure the temperature of small samples, particularly, say, in melting point apparatus or a boiling point test that you're doing. Now, heat capacity is also a factor. Materials with large heat capacity require more heat to change their temperature than materials with low heat capacities. Heat capacity, also called specific heat, is the amount of heat in BTUs or calories or joules required to raise the temperature of a unit mass of substance by 1 degree. And water, interestingly, has one of the highest heat capacities of any known substances. Here's the value of the heat capacity of water in calories per gram Celsius degree. It's 1. Not surprising. Water is a material that's used as a standard for heat capacity, so its value is set to 1. It's interesting that ice has half the heat capacity of water, and likewise steam. Here's a nonpolar liquid, ethanol. Here's wood, with less than half the heat capacity of water now. And glass is only a fifth of the heat capacity of water, and metals are generally even less than that. Look at mercury. Mercury has a heat capacity 30 times less than that of water. So if you have a mercury bulb sensor in a thermometer, it does not require much heat to cause its temperature to change because it has a low heat capacity. It's not going to disturb the temperature of the sample much, or minimally so. Now I have a short exercise here. I'm asking you to convert 1 calorie per gram Celsius degree heat capacity to a different set of units, BTUs per pound Fahrenheit degree, given that 1 BTU is 252 calories and 1 pound is 454 grams. So let's do that. How many BTUs per pound Fahrenheit degree is equal to 1 calorie per gram Celsius degree? So we want to convert calories to BTUs, grams to pounds, and Celsius degrees to Fahrenheit degrees, which means we're going to need 3 conversion factors. And we want to wind up in units of BTUs per pound Fahrenheit degree. So to convert calories to grams, we're given here that 1 BTU is equal to 252 calories. So I want to cancel out calories, put those in the denominator, and go to BTU, so make sure that's in the numerator. And we just said here that 1 BTU is 252 calories. So just follow the units. So calories will cancel. We would now have units of BTUs per gram Celsius degree. So next we want to cancel out per gram and go to per pound. So put grams in the numerator to cancel grams in the denominator, and put pounds in the denominator. And we're told that 1 pound is 454 grams. So 1 pound is 454 grams. Per grams have canceled. We now have units of BTUs per pound Celsius degree. Finally, we'll want to convert from per Celsius degree to per Fahrenheit degree. So let's put Celsius degrees in the numerator and Fahrenheit degrees in the denominator. Recall from the last lesson that 1.8 Fahrenheit degrees is equivalent to 1 Celsius degree temperature change. So my units now are BTUs per pound Fahrenheit degree. And if you divide 454 by 252 and 1.8, you'll find that is equal to 1.00 BTUs per pound Fahrenheit degree, is equal to a calorie per gram Celsius degree. Again, not surprisingly, because water is a standard for calorimetry, and so its value is set to 1 on both of these scales. So this is summarized on page 7. To minimize the disturbance of a sample temperature, the following should be true. The sensor mass should be relatively small compared to the sample mass. The sensor material should have a small heat capacity, ideally something like a metal. The sensor should be insulated from its surroundings so we're not gaining or losing heat to the surroundings. The sample conducts heat readily to the sensor. It has a high heat transfer coefficient so that it'll equilibrate quickly, and the sensor should have a large surface area. Not large mass, but large surface area. And we're going to look at a variety of temperature measuring devices. We'll start with, I guess, what you might call a trivial one first here. Basically, any property that varies consistently with temperature can be used for temperature measurement. And one of the simplest temperature measuring devices that's used in industry is called a thermal strip. It contains a polymeric liquid crystal that changes color reversibly with temperature changes. We use these in electrical panels in industry. If a panel is getting hot, that would be indicated by a color change on the strip. We see them domestically as fever strips. Here is an example of a color change with temperature. Here is an aquarium thermometer, a thermal strip on the side of the aquarium glass. Here's a thermal strip that measures temperature. And here's a rather novel application. We can have a visual indication of the temperature of the water from the shower head with a thermal system built right into the shower head. Here's a list of the temperature measuring devices we're going to study in this chapter. So we have resistance temperature detectors called RTDs. This is basically a coil of wire. It can be copper or some other metal. We'll look at thermistors, which are metal oxide mixtures. We'll look at thermocouples. Two dissimilar metals are joined. We'll look at the Wheatstone bridge circuit, bimetallic devices, filled thermal systems, and of course our familiar liquid and glass thermometers, and finally optical and radiation pyrometers. And of these 8 types of temperature measuring devices, the first 3, thermocouples, RTDs, and thermistors, are preferred in industry because they can be connected to electronic control circuits. That is, they produce some sort of electrical measurement, and therefore they can be used not only to measure temperature but actually control temperature by the addition of steam or cooling liquids. So they're very important in industry. On page 8, we're going to look at the first of several types of industrial thermometers. This first one is called a resistance temperature detector, an RTD for short. It's a very simple instrument. In this example, I have a coil of copper wire that's insulated. The ends of it are connected to a multimeter which is measuring resistance in ohms. As you're likely aware, copper is one of the best conductors among metals, second only to silver. And so it'll have a very low resistance, but it will be not zero, it'll be measurable. And it turns out that the resistance of metals increases as temperature increases. So as this heats up, the resistance will increase. Provided that response is measurable and consistent, we have the basis for an electric thermometer. Metals chosen for RTDs should have corrosion resistance, they should be high melting, and have a linear R versus T relationship. And I've sketched a few here in this picture. Platinum is accepted as the standard by the International Committee on Weights and Measures for temperature accuracy. It is non-corroding, it's high melting, and has a linear range from -200 up to 1850 degrees Celsius. As you start to think about that and compare it to the familiar glass thermometer, you can appreciate why these types of temperature measuring devices are important in industries where very high, and very low temperatures need to be measured. Tungsten, nickel, and copper are also used, and they're less expensive. Nickel, as you can see, is not linear over its entire range. And copper has limitations. It's useful for low temperature measurements because it'll oxidize at higher temperatures. There's a variety of formulas that have been used to fit resistance temperature relationships. We're going to use a simple one that works over moderate temperature ranges. Here's delta R, the change in resistance, is equal to alpha R sub 0 delta T. Alpha would be the slope of this line. That would be the temperature coefficient of the particular material. Some respond more than others. R sub 0 would be an initial temperature, typically 0 degrees Celsius. And then delta T is the change in temperature. So let's take a look at this equation in a little more depth here. I'm going to say delta R is equal to alpha R sub 0 delta T. Now I can rearrange this a little bit here and say, let's say delta R over R sub 0 is equal to alpha delta T. And you can see that this is the equation of a straight line. Y is equal to mx. So if I plot this, if I plot delta R over R sub 0 versus delta T, I'll have a straight line going through the origin whose slope, alpha, is shown here, and that is called the temperature coefficient. It'll be unique to each metal, and they have its own temperature coefficient. Let's work with this a little bit further. I can write delta R as R minus R sub 0 equals alpha R sub 0 delta T. Let's transpose R sub 0. We'll say R is equal to R sub 0 plus alpha R sub 0 delta T. Let's factor out R sub 0. R is equal to R sub 0 times 1 plus alpha delta T. Let's rearrange this a little further. We'll say R over R sub 0 equals 1 plus alpha delta T, which you can also recognize as being the equation of a straight line. Y is equal to m times x plus b. If we were to plot this, R over R sub 0 versus delta T, when again we'd have the equation of a straight line. This time the intercept would not be the origin, it would be 1. And again we'll have a temperature coefficient, alpha, which reflects the response of the particular metal in use. Two very easy forms of the equation to use, and we'll use these to solve a few problems with. Just before we do that, let me read a little bit more. One of the limitations of RTDs is that they require an applied voltage to operate. That is, you must apply a voltage through the wire to measure the resistance. And when you apply a voltage, that generates a little bit of heat, and we're trying to measure temperature, and so this self-heating effect requires compensation. But that's generally done electronically. The accuracy of RTDs is quite good. It's anywhere from plus or minus 0.01 to 0.1 Fahrenheit degrees. That is really sensitive. All right, so problems 5 and 6 at the end of this chapter. Let's do those to get some practice using RTDs in calculations. Take a look at page 29. We have two problems related to RTDs. Problems 5 and 6. In problem 5, we're told that a copper coil with a temperature coefficient alpha of 3.9 times 10 to the minus 3 per Celsius degree has a resistance of 5 ohms at 0 degrees C. We're asked to calculate its resistance at 85 degrees C, and then calculate the temperature difference that would produce a resistance of 3.20 ohms. I'm going to start by writing out the data given and the equation. So for number 5, we're told that a copper coil has a temperature coefficient alpha equal to 0.0039 per Celsius degree. We're told the resistance is 5.00 ohms at 0 degrees C. Well, that would be R sub 0 then. R sub 0 is the resistance at 0 degrees C. We're asked to calculate the resistance at 85 degrees C. Let me write the equation down here. R is equal to R sub 0 times 1 plus alpha delta T. And we're asked to calculate R, so that's a good formula for that. R sub 0 is given as 5 ohms. R is equal to 5.0 ohms times 1 plus 0.0039 per Celsius degree times delta T. So what's delta T here? Well, delta T will be 85 Celsius degrees, because that's 85 is the current temperature minus the reference temperature of 0 is 85 Celsius degrees. It's kind of neat that the reference temperature is at 0, so the final temperature is in fact numerically the same as the temperature difference. This will be 85 Celsius degrees. Celsius degrees will cancel for us. This is a dimensionless term in the brackets. So R is equal to 5 ohms times 1. This term here, 85 times 0039, is 0.3315. Plus 1 is 1.3315. And resistance then works out to be 6.66 ohms. All right, so let's just write this down in anticipation of part B. We have temperature and resistance. At 0 degrees Celsius, our resistance was 5 ohms. We've just determined that at 85 degrees C, the resistance is 6.66 ohms. And in part B, what temperature difference would produce a resistance of 3.2 ohms? If we have 3.2 ohms, what's delta T? Well, delta T would be the difference from 0, so delta T would be essentially the same as T, at least numerically. Let's calculate delta T. for R is equal to 3.2 ohms. Delta T is equal to T minus T sub 0. And as I mentioned, that's T minus 0 degrees C, which is then really just T, which makes it kind of nice for us. So delta T is numerically the same as the final temperature. All right, so R is equal to R sub 0 times 1 plus alpha delta T. Let's solve for delta T. Let's rearrange. We can say R divided by R sub 0. Let's subtract 1. And then that whole thing divided by alpha will be delta T. So in our example here we have delta T will be equal to 3.2 ohms divided by 5.0 ohms divided by the temperature coefficient 0.0039 Celsius per Celsius degree. And this numerator is minus 1. So this turns out to be 0.64. Subtract 1 divided by 0039. This works out to be minus 92.3 Celsius degrees below the reference temperature. With the reference temperature is 0, so that temperature is minus 92.3. Now we could also solve it using the other form of the equation, delta R equals R sub 0 alpha delta T. Let's rearrange for delta T. We'll have delta R over R sub 0 times alpha is delta T. So we'll have delta T is equal to, now delta R would be 3.2 minus R sub 0, which is 5.0, divided by R sub 0, which is 5.0 ohms, times 0.0039 per Celsius degree. Delta T works out to be negative 1.8 over this denominator, 5 ohms. This is numerator is ohms times 0.0039 per Celsius degree. And that gives us minus 92.3 Celsius degrees, same as before. There's nothing wrong with these formulas. It works fine, but if it was me, I would use linear regression on the calculator. We have here two data sets that are linearly related, so why not use linear regression? Just go to mode 1, which is stat, and then choose 1 again, which is linear regression. Enter your data. It have 0, then the XY key, 5, and depending on your calculator, press the data key. And the second data set, you'd enter 85 and the XY key, followed by 6.66 and the data key, again depending on the calculator you're using. Then you would want to enter the value of 3.2 ohms and press second function x prime, and that'll give you minus 92.2 degrees Celsius. That's simple. Linear regression. All right, so that's problem number 5. So problem number 6 says calculate the resistance of a carbon conductor at 80 degrees C, given that the temperature coefficient alpha is negative 0.5 times 10 to the minus 3 per Celsius degree, and R is 240 ohms at 0 degrees C. One of the things that stands out here is the fact that this temperature coefficient is negative, not positive. And that's because it's a carbon conductor, and carbon is a non-metal. We've been looking at the relationship between metals and their temperature coefficient, but this is a non-metal. Let's write down what we're given. So for carbon, its temperature coefficient is negative 0.0005 per Celsius degree. And the resistance of carbon at 0 degrees C was 240 ohms. And that would be, therefore, R sub 0 is 240 ohms. And we're asked to calculate the resistance at 80 degrees C. We can simply use the formula R is equal to R sub 0 times 1 plus alpha delta T, because we're looking for R. R is equal to 240 ohms times 1 minus 0.0005 per Celsius degree times delta T. It would be 80 Celsius degrees. So R is equal to 240 ohms. Now 0005 times 80 works out to be minus 0.04, and therefore this subtracted from 1 is 0.96. R therefore is equal to 230, and I better carry an extra decimal here so I can distinguish, 230.4. So let's write down what we got then. We're saying T and R at 0 degrees C. We're given that R sub 0 is 240 ohms. We've just calculated that at 80 degrees C. The resistance actually drops to 230.4 ohms. So as the temperature is increasing, the resistance is actually decreasing. That's not surprising, since it is, in fact, a nonmetal. Let me just quickly sketch this. So when we plotted R over R sub 0 delta T for a metal, well, we had something like this. And alpha was positive. But now when you look at a nonmetal, we have something like this. Alpha in this case is negative, and that's for a nonmetal like carbon. It's the graphite form of carbon that conducts. And that's it for RTDs.